Hello dear students, I hope you are enjoying my online classes. Myself Ashish Sharma, your physics teacher, and in this video I will continue with the chapter 9 which is already going on. The first half of the chapter 9 we have discussed in first lecture, and in the second lecture we will discuss the second half of chapter 9. First four topics were discussed in my first video lecture, and those topics were force and motion, Newton's laws of motion, action and reaction forces, and inertia of body. The remaining four topics of this chapter 9 I am going to discuss with you in this video lecture. So the fifth topic of this chapter is inertia and mass. Inertia and mass are similar terms, but they are not same. Mass is the measure of inertia. Greater the mass, greater the inertia. But inertia is not mass. Inertia is the tendency. We calculate inertia, but not in class 9th. We will calculate moment of inertia in class 11th. And moment of inertia is defined as mass into square of radius. So for class 9th, you understand inertia in three subtypes. That is inertia of rest, inertia of motion, and inertia of direction. These three inertia are there, and according to the concept of inertia, the first law of Newton, or the law of inertia, states that any body for having change in its state requires external force. That force is required to change the inertia of the body, and body does not want to change its inertia. Greater the mass, greater the inertia. While mass is the measure of quantity of matter, the unit of mass is kg. Mass is related with the inertia, but mass is not equal to inertia, as I told you. If we consider the equation F is equal to ma, where a is the acceleration and F is the force applied on object and m is the mass of object, then by definition this mass is the inertial mass of an object. Inertial mass is equal to applied force divided by acceleration of the object. That is known as inertial mass. But as we know that gravitational force weight W is equal to mg, where m is the gravitational mass, which is again equal to weight of an object divided by acceleration due to gravity. So these two equations shows that both the masses are force divided by acceleration and they are same. Inertial mass of an object is equal to its gravitational mass. While we use gravitational mass as unit of our mass, the same definition can be applied for inertial mass. What is the difference between these two statements? Suppose this object is having mass of 1 kg and acceleration due to gravity is g. Let us take value of g approximately 10 meter per second square. So this 1 kg mass has a weight equal to 10 Newton. 1 kg into 10 meter per second square, 10 Newton. So 10 Newton force is required for keeping the 1 kg object mass in its position. And by this definition, the weight is 10 Newton and acceleration due to gravity is 10 meter per second square, and the mass, gravitational mass, is 1 kg. How come this mass is compared with inertial mass? Now consider again this mass in space with without any presence of planet or any star system. In empty space, consider this 1 kg mass only. Now if you will apply a force of 10 Newton on this object, then this object will start accelerating with an acceleration which is again equal to 10 meter per second square. So if you will apply a force of 10 Newton on a mass of 1 kg, then it will start accelerating with an acceleration 10 meter per second square. So again from this definition, mass again is 1 kg. So if you will apply force 1 Newton in space, it will accelerate with 1 meter per second square. So inertial mass is defined as the ratio of force to acceleration. And gravitational mass is also a ratio of weight to acceleration due to gravity, and we found that both the masses are same. Let us move to our next point, momentum, which is very important from the perspective of Newton's second law of motion, and we have already studied Newton's second law of motion. Momentum, we represent it by symbol P. It's a vector quantity. It is defined as total quantity of motion in an object, also defined as product of mass into velocity. It's a vector quantity. Its unit is kilogram meter per second, and according to Newton's second law, as we have studied, F is equal to rate of change of momentum, P2 minus P1 divided by time taken. And we already derived this relation that F is equal to mv minus mu divided by t, taking m common, v minus u by t, or F is equal to ma. So this equation not only expresses Newton's second law, but this is also a characteristic equation for defining acceleration, which is our next topic, force and acceleration. So this is momentum, and momentum conservation we are going to discuss in next topic. Moving forward, let me discuss with you momentum conservation first, as we just have discussed the definition of momentum. Elementary idea of momentum conservation. Momentum conservation is very important concept in physics, and a clear understanding of this concept is very important. What do we actually mean by momentum conservation? Momentum conservation का actual मतलब क्या है? Momentum conservation का मतलब ये है, I will first write its definition. What do we understand by momentum conservation? Total momentum of a body or momenta. Momenta is plural form of momentum. So total momentum of a body or momenta of a system of bodies will remain constant until unless any external force is applied. जब तक हम कोई बाहर से एक्सटर्नल फोर्स अप्लाई नहीं करेंगे, किसी बॉडी या सिस्टम का जो मोमेंटम है वो चेंज आपका नहीं होगा, वो सेम रहेगा, कांस्टेंट रिमेन्स, विल रिमेन कांस्टेंट, विच मीन्स अगर वो मोमेंटम जीरो है तो वो जीरो रहेगा, अगर उसकी कोई वैल्यू कांस्टेंट पॉजिटिव वैल्यू है तो वो वैल्यू कांस्टेंट पॉजिटिव रहनी चाहिए, अगर उसकी वैल्यू कोई कांस्टेंट नेगेटिव है तो वो कांस्टेंट नेगेटिव रहनी चाहिए, लेकिन वो कांस्टेंट रहना चाहिए। और जीरो जो है हमारा वो भी कांस्टेंट के अंदर आता है, ये बात आप लोग यहाँ पे याद रखें। तो आइडिया ऑफ मोमेंटम कंजर्वेशन इज की टोटल मोमेंटम ऑफ अ बॉडी or momentum of a system of bodies will remain constant until unless any external force is applied. Now let me give you a number of examples which shows that how momentum of a body or system of bodies remains conserved, and that is known as momentum conservation. The most famous example of momentum conservation is recoil of gun. If we fire a bullet from a gun, then what will happen? The bullet is placed inside the barrel of gun. I will show the bullet with the black color. Let us say mass of the bullet is small m and mass of the gun is capital M. Okay, please pay attention. Observe carefully. As the gun is at, let us say both initially gun and the bullet are at rest, so velocity of this system is 0. So what is the momentum before firing or before shooting? Before firing, let us say momentum is p1 and that is equal to m plus m, where now it is a system bullet plus gun small m plus m into 0 velocity, momentum is equal to 0. This is our first equation. And because the value is 0, there is no question about in which direction this momentum is, either it is positive or negative, there is no significance of it because it is 0. Now what will happen after firing? जब हमने बुलेट फायर किया, now your bullet is moving with velocity v in positive x direction. So now bullet is no more inside the gun. Bullet is moving with m mass, bullet is moving with velocity v, and the gun will rebound with velocity u. How to calculate u? How to apply momentum conservation in this situation? So in second situation, after firing of gun, as bullet is moving in positive x direction, the velocity of bullet is plus v in vector form, while velocity of u is going to be minus u because it is in negative x direction. What is the momentum of bullet? Momentum of bullet is m, let me write it with, okay, can you let, no, doesn't matter, mv plus momentum of gun. As mass of gun is m and velocity of gun is minus u, so you will get this thing minus mu. This quantity is your p2. Momenta of system of gun and bullet after firing is small mv plus minus m into u. This is our second equation. Now after calculating the momenta before firing of gun and after firing of gun, as no external force is involved, so by the definition of momentum conservation, P1 must be equal to P2. P1 must be equal to P2. As your P1 is equal to 0, it must be equal to P2, that is mv plus minus mu. Or in other words, we can say mv minus mu is equal to 0, or by taking mu on the other side, mu is equal to small mv, or u is equal to small m into v divided by capital M. This is your very famous relation for calculating recoil velocity of gun. Go through this. So there are many more examples which demonstrates momentum conservation, like if a person is standing on a skateboard which is indicating very less friction or almost no friction, if that person throws if the mass of the person is capital M, and if this person throws some small mass m with velocity v, then the entire setup of this skateboard and this person will move backward with the velocity u, having same magnitude mv divided by m. Okay, so there are other examples of momentum conservation. When we are stepping on the shore from the boat, then the boat moves backward as person is trying to jump on the bank of the river or the shore. And the water sprinkler, they only start rotating when water is coming out through them for maintaining the conservation of angular momentum. And in the same manner, your action and reaction balance are also equal and opposite, which are also associated with momentum conservation. And about this force and acceleration, we have discussed it already in Newton's second law of motion, and in chapter 8, force is an external push or pull which changes the state of motion of a body or size or shape of the body or try to do so. And acceleration is defined as rate of change of velocity, which we have already discussed. It is just mentioned in the chapter later in syllabus, but these sections are already discussed. So if you are having any doubt, you can ask your doubts in the comment section of the video, or you may also contact me on WhatsApp. Thanks for watching. Take care. Bye.